We good? Yeah, cool. Thank you, Jeremy. We, I guess as the faculty dinner, I noted we started at the same time, but we finished at very different times. Jeremy was on the fast track. Um, I'm going to talk a little bit today about some work in contextual reinforcement learning, and I think that bears on some problems in social interaction, as well as some work that's clearly in the social domain that I've done in collaboration with the Development Hall Lab at Berkeley. And all of this work is sort of focused on, stemmed out of work actually that I did, starting the end of my first year of graduate school after I got out of the cells and dishes stuff. And that was all just trying to answer this like pretty basic question of like how, we use a new experience to shape our future behavior. And the cartoon version of this is like we wander around our world, we use our expectations about the world to guide actions. When we take an action, we get some feedback on that action, and then have maybe an opportunity to revise the expectations that we had about the world that may have led us to trouble. And in some cases, we may take that opportunity to heart and revise our model of the world, our expectations about the world, and change our pattern of behavior going forward. In other cases, we might not, or might do so less, and persist in the same patterns of behavior going forward. And so in my lab, we're interested in both, why in some situations and experiences will shape our patterns of behavior a lot, like change the way that we act in the future. And other situations, they don't. And also we're interested in this idea of how one experience in one situation might affect my behavior in other situations in the future. And we're also interested in this idea that's sort of alluded to by the normal person scientist here. Why do some people learn one thing from an experience and maybe, change their behavior in a certain way, and other people take a completely different thing away? And these are a lot of questions, but, our only sort of, life preserver in this sea of questions is this idea that maybe, an idea that didn't originate with me at all, but maybe what, we're doing when we learn is using the past in a way that allows us to make a prediction for the future. And so we can sort of think about this really, silly cartoon problem. It's this, arrow of time here where we get some, information, and that information serves to help us make a prediction about what's going to come next. And maybe we get a lot of experiences and we get a lot of information, and, learning would be useful if it could somehow, represent this information in a way that allows us to predict the outcomes of our actions and thus take the actions that would be most beneficial to us. Of course, in this case, there's, maybe not a lot of the complexity of the world, but if we, in the general case, we may not want to represent everything, but one thing that we certainly want to pay attention to is outcomes of our actions that have some sort of, valence associated with them. Things, actions that make things better or worse seem particularly important to pay attention to. And typically, we're not going to get completely accurate feedback on these actions. So often, an action might yield a reward in one situation. So reward would be the reinforcement learning terminology for this positive balance feedback. But it may not, be as fruitful in a different situation. So if we want to make a good prediction in the face of this sort of variability, the simplest thing to do, and in fact, the best thing to do is just take the average of the data that we've seen so far, right? So this is what I'm showing down here. And it turns out if we just rearrange this equation a little bit, we get this learning rule down here. And it says, I'm going to update my expectations about the world according to this thing here, which is called the prediction error. It's just what outcome I got minus what outcome I expected. And I'm going to weight that by, if I'm going to take a running average, 1 over the number of data points I have. And, in principle, we can do this, and we do see that learning obeys some sort of dynamics that look a little bit like this. But often in the reinforcement learning literature, what we'll do is just call this thing a learning rate, and we may set it constant, or we may adjust it in different ways to sort of match behavior. Okay, but so if this rule were all that we had, and we could only describe, we could only learn actions that were rewarded, then reinforcement learning wouldn't be particularly useful. In this sense, it's like a purely supervised thing. We get the outcome, and then we know to expect that outcome, right? The thing that makes reinforcement learning useful is that we can use it to learn things that weren't themselves rewarded. And to sort of build that level of complexity into the model, we have to consider that I can, that actions might have a different value when taken at different states of the world. So we have to consider the possibility, that I can be in different states. And I'll try to, define that a little more in a second. But just imagine now, this is my house, this is the ice cream shop. I, want to learn that, getting ice cream is good. And so I should follow this path to the ice cream shop. But in order to do that, I have to, take this action, which is not in and of itself rewarded, right? And so a set of algorithms that allows reinforcement learning to solve this sort of problem is called temporal difference learning. So in temporal difference learning, we have, not only I think I'm going to have some boxes, so I'll use my boxes. We have not only the value of a particular action, but we have a value of a particular action in a particular state, right? And that's the thing that we're going to keep track of. And we want to update it on each time we get some feedback. But we're going to add something into the prediction error equation. And the thing that we're going to add is essentially how good was the state that we got to. If we got to a really good state from taking an action, then we're going to sort of say, hey, that action that I took was good. If we get to a really bad state when we take the action, we're going to say that's bad. There's another parameter in here to, the discount factor, which affects, how much we care about future stuff versus present stuff. But that's the basic idea. And, so now this entire term is the prediction error. And, what we can do is learn a gradient, a value gradient that goes up to the ice cream shop. And now I'm at my house, I can just sort of follow this value gradient. The way I learn this gradient's a little stupid and slow. I have to bounce into here, get a positive prediction error, and then bounce into here, get a positive prediction error, and bounce into here, get a positive prediction error. And that seems a little silly, but in modern sort of reinforcement learning, sort of solves that problem with a particular strategy called replay that I think Matt is going to talk about in his talk. I'm not going to talk about that at all here. We're moving on to, a question that, I'm very interested in, which is, okay, clearly these states are useful, and they're useful for transferring knowledge across situations. But what are the states? It's easy in the ice cream shop example. We can do spatial, but even like, adding complexity to the ice cream shop example, well, okay, I could do every block. I could do like every half a block. How many states should there be here? And, intuitively, well, if we represent things in tabular form, which just means discrete states, then if I, have these two states that are, if I separate states, then I'm basically saying I'm not going to share information across them. And so we can ask this question: are these two locations, are the action values I'm going to get in these two locations similar? Should I share knowledge across them? What about these two locations? And we don't have to think about it necessarily in like a discrete sort of way. We can say, well, maybe we have representations in the brain that might be continuous and might live across these, discrete locations that, might share knowledge across these different locations to a different degree. And there's, learning algorithms that we can use to, instead of updating the value of an action from a given state, they'll update the weight of a particular basis function in predicting the value of an action, right? And basically it's just a continuous version of the problem that I showed before. Great. But we still don't know, what a state should be. Should they look continuously like this and not share much across states? Should they be like this and share more? And it gets more complicated, right? So like that space, but like we work a lot with rodent labs who like train animals to do like, olfactory navigation tasks where like, being in a certain location, if I had just smelled a banana smell, means I have to go one way. And if I just smelled a flower smell, I have to go the other way. I don't think they really use flower smells, but imagine you have to carve up a state space in a more complicated way for, not just space, but other features. Also, we, have to solve these sorts of generalization problems. So would we represent the layout of like a grocery store in the US using the same function that we represent a grocery store in France, I think that one is. If I learn that peanut butter is near jelly in the US, will that knowledge transfer here? And will I be able to sort of apply the same policies for, going grocery shopping across these two things? Like if I want to do that within the reinforcement learning framework, there has to be some common representation, or else I'll learn something here and I have to relearn it from scratch when I go here, right? And another problem that our lab is particularly interested in is how we represent time. So these are the years since I have had a lab, 2019 through 2023. You might imagine that I'm like slowly accruing knowledge about how to do my job. You may not imagine. I don't know what you're imagining. But you could imagine that, I'm like, learning one policy across these time points, right? And that makes sense based on what I said about averaging data, right? Well, like right in the middle there, we had this thing that happened in March 2020, we had COVID. So the sort of policy that I was, applying back here involved like things like this. Like I think in February, I took my kids to this crazy water park that was hitting people. And then like, a month later, we were doing things like this, like holding meetings, like with 6 foot spacing and masks outdoors. Clearly, people were able to completely change their behavioral policies really rapidly here. And, one way that they might do that is through, separate state representations for different temporal contexts. And an interesting thing about this is, people might represent these temporal contexts differently, right? So like, some people might have bounced into the, COVID context and never bounced back, whereas other people might have bounced back. And when people bounce back is completely different, right? There's a lot of individual differences. Yeah.
So if time is a feature that we like care about and incorporate into what we think of as a state, in one sense, you can never really repeat a state because like the time won't be the same.
Right.
So is that like kind of an unsolved mystery or something this framework takes into account? Or
right. So if you think about the prediction framework, as long as you know something about the how the environment is generated, if you know the structure of the environment, then you can say, well, things, the mean has been stationary for, X number of trials, or I have a probability distribution over the amount of time that things have been stationary. Based on that probability distribution, I think whatever the value function should look like this, or the parameters of the world look like this. But yeah, like you could have this. So there's a model complexity thing, right? You could have a super complex model that's like, oh, this is the feedback for timestamp X. And then like, this is the feedback for timestamp X plus 1. And that model will never generalize forward, but like you could feel like maybe you're doing well. And we actually like think that actually might be in play, and specifically in like certain clinical disorders. Yeah.
These states are all discrete, right? And I think maybe like just going down and makes sense. Situation where you have step function from about 6 feet apart. But the second transition for most people probably is not I'm going from pandemic to non-pandemic.
Yeah.
And that, like, even in the first thing, it's like you can imagine that it's not discrete, but it's like just a very deep transition curve or something like that.
How
do you, like, is there a way to have non-discrete states?
Yeah. I mean, so like so we're gonna maybe so I'm actually not going to talk about that at all, but I will just say, like, yeah, you can model a generative function of the world, that how the world generates data. And if that generative function is, has these discrete transitions, you'll get dynamics that they don't actually look discrete when you look at them, because it's like, it's using discrete computation, but each moment at a time, it's like, oh, I'm 20% sure we went back to the, like, regular, I'm 30% sure, the actual learning across possibilities is incremental.
You would still have discrete states, but you have like belief distributions over these states.
Yeah, exactly. But then you could also instead model it as a drifting drift process. So like Hayam Pire, which I may be pronouncing wrong, but has like a nice generative model that's analogous to a lot of the stuff that we've done, but instead of discrete, it's continuous. And you can actually bake a lot of continuous stuff into the framework that we use. But like the real question, which I think, goes beyond, I think, what you just asked, but is clearly underlying it, is like, what is the structure of the world, and how do we learn the structure and learn to use it at the same time? And that's stuff that we're also really interested in, but that's like half baked and not ready for presentation. Okay, so this is time. We're also interested in social spaces. So like, if I learn like some social action is good, like with this guy, whatever, like, should I apply it with that other guy? Maybe situations like, if I learn that this guy is gonna screw somebody over in the snowdrift game, will he also screw somebody over in Prisoner's Dilemma? Apparently, those are two different variants of social games, but couldn't tell you exactly what the difference between them is.
Consider those states.
Yeah, so that's the question, right? So how do we break down? I think we need some way of learning something about this, and and using it to inform our understanding of this. So if we consider them completely different states and use some sort of learning framework that's discretized across states, then we don't get any of that. Feels like we want to do that, but how and how much, I think, are open questions that we actually, so Jeroen Ben-Bar, who is postdoc with Oriel, I think addressed pretty well. And I'll go in more detail into the last three things that I showed.
I would imagine you'd have similar policies across these two games, right? If they're kind of demanding the same action.
Different policies across these.
Or the same.
So I guess the question is, I am learning about you, seeing you play this Prisoner's Dilemma. You totally defected. And now we're playing but the question is, our cars are parked next to each other. We've got shovels. Like, do I play this snowdrift game with you, or do I try to flag down another car and get somebody else, right? Like, I think that ideally we when we learn something here, we learn something not in some observable state space, but we observe something in some latent state space about like sorts of things that go on in Nina's head when she's like, making social decisions. And then when we've like updated our understanding of what's going on in Nina's head, then we have sort of we can either use an RL framework, we use automatic transfer, where it automatically transfers to what would happen in this other situation, or we can do something like Day is working on wherever he is, where it's like sort of a Bayesian framework, where you're sort of like, inferring what's going on, what would happen in this other situation.
I guess like in terms of defining the state, like the latent state of me, for example, wouldn't change necessarily. Still don't trust me.
Yeah.
And either of these circumstances, even though the game has changed.
Yeah, the motive. So the motive is not observable. So, but I basically, if I'm, you know, inferring, it's basically, I'm inferring the latent state inside of your head, which is a motive, and then learning something like that is like, what actions should I choose with a person who I don't know.
So that's the relevant state, like that's the level.
Yeah.
Kind of discretization is what you think I am.
Yeah.
Okay.
Yeah. So you basically like learn the we're learning which latent state we're in, and we're learning to map parameters of that latent state, which could be like the value of actions I can choose. Yeah.
It's like it is confusing. It's specific with this example is that here on your screen, your states look like games. But I think that in this conversation, the stuff you're learning about presumably is actually Nina. Like the target of inquiry that we try to build a model of the world of is a model of Nina, not a model of games. The games are observation. Like they're like the one observation after another observation, like different games, and you generalize over that into states of Nina, not states of games. Like you're not learning game states.
Right. I mean, but you could, so you could have, okay. Can you hold that till I actually get to, so if I get to a slide that actually shows the work that this is on, it'll be a lot easier to you know, clear up that question. So I am way over on what I prepared because I'm already at 20 minutes and I haven't actually got to data. But I'm gonna still give you some picture of, you know, each of these sort of three projects, and I'm probably gonna fly through a lot of stuff. So if people are sort of interested in any of the three, they're, you know, I'm here for, you know, another 3 days, I guess. How do we break up time? You know, we can't measure, we could maybe measure people in real life across longer time scales, but our lab hasn't done that. What we do is bring people in the lab, have them perform games, have embed temporal structure in those games. So one game, you know, one backstory for this sort of game is we'll have, you know, a helicopter up in the sky and it's dropping bags that contain money. The participant on each trial, they want to move a bucket under the helicopter so they can maximize their money and take home some bonus payment. So that's easy because they see the helicopter. The bags sometimes follow left, sometimes follow the right, so they're not a perfect predictor of where the helicopter is, but the best place to move buckets under the helicopter. Then we have them play this version of the task where everything's the same except the helicopter's occluded. And they then have to infer the position of the helicopter using the, you know, placing their bucket. And we can give the helicopter any sort of dynamics we feel like. So, you know, we can, you know, model this as sort of the helicopter's position as a latent state, which the participant doesn't get to see, but it gives rise to a, you know, a bag location, which the participant does, you know, get to see. And yeah, we can do Bayesian inference to see what you should do, and then see what participants actually do. And two particularly interesting temporal structures are these ones. So one is a change point environment, so where the helicopter discretely moves to new locations. And in the green points, you can see sort of like locations where the gold fell, and in you know, orangey brown where the participant actually placed their you know, bucket on each route. And the thing to notice is like what happens after these transitions. And you see only one error, the participant basically just completely adjusts, right? In contrast, if we, you know, bake in a different temporal structure where the helicopter is slowly moving around, like drifting, but then occasionally there's like a huge outlier, the participant will completely ignore those outliers because, you know, as you can see, it's like this outlier is not predictive at all of the future, right? So how does the brain do this? I guess maybe what I should say first is like, you know, that was one participant, but if you look across participants, we can sort of characterize learning by the degree to which someone moves toward the most recent bag, where, you know, 1 is all the way and, you know, 0 is not at all. What we see is on change point trials, you get a huge increase in how much people are going to learn. And in oddball trials, you get a huge decrease in how much people are going to learn from the outcome. Right? And these data were actually collected while people were set up for EEG. And it turns out that we have no problem detecting these like surprising events from an EEG signal. And the signal that seems most related to these surprising events is like a P300 signal. And the idea that we had before doing this study was that maybe, what the brain is doing is having a control knob on how much you listen to the new piece of information. That seems to be wrong. So it turns out that, other people had observed this orange curve here where certain signals positively track with how much somebody learns from a piece of data. But what we see is that this sort of tracking learning actually flips directions completely in a different temporal structure where you're supposed to ignore the thing that was surprising. All right, so now I'm gonna have to do some skipping of stuff so as to not spend a crazy amount of time. The idea that I'm going to try to say we shouldn't pay attention to is the idea that you're really just giving importance to new experiences. And instead, what I want to introduce is the idea that you're breaking up time, right? Because we can think about these different change point and oddball conditions as just different temporal states. And the only difference between them is a transition function. And it turns out that we can come up with, we can use this idea to sort of dynamically adjust the state representation in a neural network. So like the, context that learning is getting attached to. And if we just update it according to these transition functions, we can get a network to, learn better from new information. So in this case, what we did is we saw a change point and the network basically said, we're going to activate a new state representation. We're going to attach learning to that new state representation. And by the time we get to the next trial, we're going to make a prediction by activating this node and then immediately going to the location that we just saw an outcome, right? And if we teach the network to do the oddball variant of the task, but we give it some information about the structure, then we get this sort of behavior where we see a surprising event. So we see this trial, and then all of a sudden we activate a new state representation. We attach the learning to this new state representation. But because in the oddball case, we know that we tend to go back to the regular trial, we then activate the state we expect the next trial to be in. And now we've sort of prevented interference from that oddball. Basically, we're now going to make a prediction that was, where the weight of the network is not sort of encumbered by this learning from an outlier event that's basically going to be a distraction from where the true need is. So this was all work done by Nilüfer Razmi, who's a graduate student in my lab. And she, showed how to make this work, showed how to improve on, performance of a basic neural network, and also to match human behavior really well. But the key result that it sort of explains is this relationship between a brain signal and learning. So like basically in the model says you have state transitions, and that's the key way that we do dynamic learning dynamics. And within the model, the size of the state transition is positively related to learning in the change point condition and negatively related to learning in the oddball condition. Yeah.
So that sounds like you're describing the network in sort of the fully learned situation, right?
Yeah.
Where it's learned, I guess, the states and the transitions between them. And
we give it the transitions. We cheat.
Right. So,
yeah.
Okay.
So we are. So right now we have a probabilistic model that can learn the transition structure, but we have not figured out how to make a neural network do that.
Right. It's a partial solution.
So, the Bayesian inference model over that is we've got all of these possible parameters of hierarchical Dirichlet process. One parameter set can give you a change point task. One parameter set can give you an oddball task. We're going over time, doing online inference, slowly learning like, oh, this one's more likely than this one. But like, in order to make that work and work for all possible tasks, we have to, in the Bayesian models, considering simultaneously a very large space of possibilities. And like, if you are an actual like brain constrained by like, when you learn a weight, it's there and you can't get rid of it, like, unless, I don't know, maybe the magic of replay, like maybe that's like, where it's at. But like, yeah, we don't know the answer to that question. That's hard. Yeah.
Is it also, so like in the learning phase of this, like, I guess if you know that there are several discrete states that are possible, then when you see the surprising events, you can try to infer what might happen next, and it's easier to understand the structure. But I guess, like, what if you don't have any priors about what the possible states are? Is it possible to learn that when you see the surprising thing that now you might want to form a new state representation?
Yeah. I mean, that's the form of the model, the Bayesian inference model is like, it's a non-parametric. Yeah, I mean, yeah, essentially, it's like a little more complex because it's like hierarchical, but that's the idea, is you can add indefinitely, but like, yeah. That's a sort of, I didn't actually put any slides on that project in here. I put way too many slides. This explains other brain stuff. I think I'm going to skip to the social because yeah.
So do you think that lower learning for the oddball events is synonymous to failing?
For hybrids.
So you do have.
Yeah. So this is like an interesting point of discrepancy, I think, between when you model it discretely versus continuously. So like, you could model things continuously and just be like, oh, like, data are unreliable, or continuously where you say like, it's not coming from a normal distribution, it's coming from a T distribution. So when I see a really extreme data point, then like, it's almost certainly like less informative than if I see a inline data point. But so I personally, I think it makes different predictions, but I think in the data that we currently have and that others have produced, it's I would say the jury's still out if either of the if people are one way or the other, or if they have an arsenal of a bag of tricks that includes both, or
Yeah.
Yeah.
I guess in both contexts it makes sense to downweight events, right? Because they're not necessarily informative of like the underlying need.
Yeah.
They just get a high noise context.
Yeah, but I guess so. The thing is, if you just downweighting the data, like the brain signal shouldn't be like. So like, I show the P300, but also like ACC bold response, very big on these surprising events, both for change points and oddballs. I had a paper in 2012 that showed like, you get huge people responses on change points, and you can, and basically they lead to increased learning. And I was really excited about that. And then 2013, Jill O'Reilly had a paper showing like in an oddball condition, almost the exact opposite result. And so why are we having huge rain responses to these things if we're like, all we're doing is ignoring them? And I think, we don't have strong behavioral ways of getting, teasing these things apart, but NoFar's model can explain all of those neural findings in a way that is satisfying. And I don't know if a version of the downweighting model that came in.
Yeah, I mean, it's interesting because it's like I see the same things if I'm comparing learning rate versus memory, right? So change point and covariance both really increase recognition afterwards. So there's some kind of attentional gain associated with those events. But the effects on learning rate or on, kind of episodic drift are completely opposite. So I've been thinking about it in terms of, perhaps like the first thing that happens, that attentional gain if you generalize on this paper, but the sort of like temporal signature that could be happening where at first you get the gain and then something else happens. But and then I think that's where the updating happens, right? And so but yeah, I mean
it also depends how you define variance, right? Because there's also this like difference showing that when you have like this volatility environment, your learning may actually increase. And it's a high variance.
right. So it's but this is I think this is the kind of point of difference is like, is it a surprising event that states versus not? So high volatility is still changes in states. Whereas high variance isn't. So you would expect that in the volatility environment, it's like a changing environment where it's actually useful to increase your learning rate. Yes, that's exactly in line with what we're saying.
Sorry, I was just getting permission that I can talk more.
Get through the rest of his.
No, you're good. I mean, it's my fault. I was, I put way too much in here. But I'm going to talk at least about one of these projects, and then so I have been collaborating with Oriel, and this is the postdoc Jeroen and former grad student Amrita, and I'm going to talk about one of those projects right now. It's like I'm going to flip a coin behind here right now. So, but so the framework that we've just been talking about with like inferring underlying states seems particularly relevant to social problems. And this is from a review that I wrote with Oriel. We're sort of comparing, the complexity of learning in social interactions to maybe some of the simple laboratory tasks that we study basic reinforcement learning in. But at least, sort of consistent with, the way I was like, sort of describing the states of Nina, we have some observable social dependencies. Like we can tell that like, these people are, whatever, have their snow shovels, I guess, shoveling snow. But we know that there's some stuff that we can't see that's probably affecting the way that they're going to behave. This, likely includes a much larger, list of things than the things that we actually have in here. But certainly we can do a better job at interacting with a person to get what we want, assuming that's our goal tonight. If we have some constraints or if we have some understanding of their underlying affect and motives. And I think I'm gonna skip Jeroen's thing and go straight to Amrita's projects. I talked a little bit about this, but Jeroen focused on this idea. Just say quickly of like, can we, set up games that are observable where we can see something about like what the situation is like for both partners and use that situational knowledge to transfer our prediction about what they would do in situation one, or our observation of what they did in situation one to situation two, even if situation two is unique from the perspective that they've never seen this exact game because the games are parameterized. And it turns out that people, are quite good at this if you give them agents that look like actual humans, and quite bad at this if you give them agents that don't look like normal humans. And you can do a pretty good job of modeling it if you assume that what they're learning is not, what to do in a specific combination of ST, which would be like each, situation is its own state, but rather what they're learning is, how much weight to give each of a set of motives. And there's cool eye tracking and there's a generalization, but I'm going to skip that. The other project I want to talk about a little bit is also was run by a graduate student in Amrita's lab, or Amrita, a graduate student in Oriel's lab, who just ran an iterative trust game. So where, participants were asked, like, how much do you want to give? They would see, this, nondescript white dude, they'd give some money, and then it would get multiplied by 4, and then he would return some money, right? And there are a few notable things. One is they played this game with a bunch of different partners. Some of them were, low reward, low return rate. Some were high return rate. Some were neutral. The partners weren't always like displayed in a row. So like, you might see, this guy here, but not see him again until here. Meaning you, in principle, might like have some interference effects for the people that you've seen between. And it turns out that actually was the case in this task. The other thing is that she had 2 variants of the same task. I'm showing the one that has the, is framed as a social game, but she did the exact same game framed as a bandits task, where it's like, instead of investing in this white dude, you're investing in a red slot machine. Okay, so the key behavioral result is that people learn faster in the social framing of the game. And you might come up with competing explanations for this. Maybe in the reinforcement learning model, you just turn up the learning rate when things are social, that's a possibility. It turns out that might not be what's going on here. So when we look closer, we see that the interference effects I mentioned are much stronger in the bandit game. And we can think about this by thinking about different state spaces that you can learn onto. Like one is just, okay, I'm going to learn a Q value of investing in each of these different dudes. But another is like, I'm just going to learn like a Q value of like investing, right? Like, because like, let's be honest, these guys are, I don't know if they would show up in the same part of your face space, but to me, those are like almost indistinguishable dudes. So that's one possibility, but and maybe that doesn't make sense to you because we have strong priors that people are different, I think. But this one might make more sense because like, a prior for like where slot machines are generated is like, might be that they all sort of are designed to screw us in the end. So maybe this model makes more sense here. It turns out when we fit models to the data that have like a parametric state space that flexes between these 2 possibilities, the social task, we fit a model that looks like there's a lot of really specific credit assignment, but the bandit task, we fit a model that's like, it's sort of, if I learn about the red bandit, I'm like also giving, some of that information to the purple bandit, right? I'm sharing information. And what I'm showing here is the fit. It turns out that we fit this model with different credit assignment after good things and bad things, which I didn't necessarily expect would matter at all, but it did. So it turns out that when bad things happen, people are reluctant to invest in anything on the next trial. Whereas when good things happen, they're more like specifically attribute that to an individual or a bandit. It's like it shows up in both situations. So there's basically I should mention that this is like an average across people, but there's huge individual differences in how people do this. And the question that we're really interested in is, can we actually see the state representations that are driving these sorts of learning in the brain? If so, we should see, well, something that represents people and bandits, but we should also see it, we should see it at time of choice and time of feedback, because it has to transfer knowledge from feedback to the next choice. But it should be stronger in the social condition. It should be stronger for positive outcomes. And it should be stronger when for individuals who seem to be using this sort of separate credit assignment rather than these guys who are using joint credit assignment. We did an RSA analysis to sort of look across the brain for signals that represented the different partners that people played with. We saw a lot of regions of the brain that actually had information about which partner you were playing with in both the slot machine and the trust games. And we found a lot of regions that showed it at both time points during feedback and choice. When we look at these regions and ask whether they show the sort of key markers of something that should that could actually be translating into behavior, we see a bunch of regions, including orbital frontal cortex, which our lab had previously identified as a marker for temporal state representation. We found stronger representations on the social game than on the bandit game, consistent with the behavior. We also found that these representations, if you average across regions, tend to be more precise when somebody gets positive feedback than when they get negative feedback. So consistent with the idea that they're sort of precisely, assigning credit for good things, but, broadly distributing credit for bad things. And then we see across individuals, the individuals who, had the most specific credit assignment also have the most precise representations, whereas the people who had the least precise credit assignment, have indistinguishable representations, I would say, sort of near chance at decoding the different faces. Okay, sorry for the packing a lot in and then speeding up a lot of the fat at the end. But the takeaway here: dynamic latent state representations provide a mechanism for inference in a complex world. Precision of cortical state representations closely track precision of credit assignment. And if you're interested in generalization about different situations, come talk to me afterward. Thank you all, and thanks the work from my lab that I talked about was Nassar, and the work that I talked about from collaboration with Oriel was Enrico. Thank you.
So this is like more of a thought experiment about what might happen if what might the prediction be if this is happening. So in the trusting, I think it's interesting to think of like people's history today, and you're trying to update your beliefs about their motivations or how they might behave with you and treat them more independently than establishing. But you're kind of playing a repeat game with them, interacting with them. But what if you thought that they were playing with each other as well, like randomly? So like, well, they're not playing with you, they might be playing with other people, and it's all happening. Some kind of simultaneous. So it's kind of like your behaviors or whatever the norms are might be creeping into other people, depending. And so it would be actually less independent because people might.
Yeah. So you're saying there's like, I have one graphical model that could explain the interference effects, but there's another graphical model that could explain the interference effects, which is like the guy who's screwing people over screwed over this nice guy, and now that nice guy is screwing me over too. Yeah. I mean, I think that's like, well, I mean, I think it would be indistinguishable in the data set we have, but I think it's a sort of interesting idea. And like, I think it's testable with the right design. Yeah.
I'm kind of curious on your thoughts about just the relationship, since you've worked in both kind of like more probabilistic Bayesian formulations and more RL-based formulations. Like, how do you kind of see the predictions of each? Because like, it feels like a lot of these models are actually like make a lot of sense in a hierarchical Bayesian kind of framework. But are there like certain predictions that they don't make when it comes to like the state generalization?
We haven't seen a ton, and I'll say my bias. So I mean, I'll state my bias that like I tend to think that the models can do a lot. Like the families of models like can really do a lot, and so it takes a lot of constraint to find something that either family like can't do. So when we've tried hard, we've usually built that bridge. And the reason we usually build that bridge is there's just such strong evidence that reinforcement learning is a mechanism of learning in the brain. And a lot of that comes from animal work, but we know that there is a reward prediction error signal. We know like the way that stratocortical, I like skip my BG slides, but we know the stratocortical architecture is set up to take such a signal and translate it into, weights, basically connecting neurons. And yeah, so we tend to start with Bayes because it gives you like a you know, like I said, like a life test. Like it's sort of like, well, these are really hard problems. Like maybe like we should figure out what a good solution would look like. But then we tend to go and use RL to be like, could you get this? Like, could you do this in a way? And you know, we'll even do like a cognitive level RL model. Then like, could you actually wire this up? Like, so I mean, I haven't found anything yet, but like, but like I guess I can't answer Matt's question on how you would do this, like you know, hierarchical tier model in like a sort of RL framework. So you know, there could be situations where
Did you run vision last set of data?
the last set of data, no, we did RL, but I mean, but the Bayes in the RL in this paradigm is the same. It's basically a Kalman filter, and the Kalman filter just converges on a fixed linear rate. So like it would differ on the first two trials, like being slightly different learning rates. I mean, it's not.
I mean, that's been our experience too. I'm just curious.
Yeah, we really have to push to get like in a framework where you can distinguish between things. And then my understanding is like then what you're breaking is ancillary assumptions. Like it's not like you're breaking the idea of reinforcement learning. You're saying, well, like if this is the state space, then it's not working. But like, well, we can, you know, use a different state space or use a different action space, or like we've got so much flexibility in these different frameworks that like, you know, I think it like I find it hard to think of like a strong inference, like where it's like, you know, I can falsify reinforcement learning with this one paradigm.
Thanks, Matt.